So today we will start with a new topic of current electricity, or you can say electrodynamics, and the topic is about the drift velocity, right? So this is about the current electricity. In the current electricity, already we studied one topic, that is the drift velocity through a uniform wire, right? So we took a uniform wire, right? So drift velocity in a uniform wire, So in the uniform wire means the uniform cross section. So this was the uniform wire having the same area of cross section everywhere. So area at this point is A, again the area at this point is A, and again the area at this point is A. So this is a uniform wire, means the cross section area throughout the length of the wire is same. So in that case, what is the drift speed of the electrons, right? So the drift speed of the electrons, Vd, right? So what was the drift speed? So the final formula we find that was I is equal to N A E Vd, right? Where I is the current flowing in the wire. So this is the current I, right? I is the current flowing in the wire. N is the total number of electrons in the wire, right? And the total number of electrons N in the wire in the metals, that was 10 raised to the power 28 per meter cube, right? Per meter cube. So in this volume, the electrons are this. Area is given A, it's a uniform area, right? This is a uniform. Now the area is uniform. And E is the charge on the electron, right? We can use Q also here, right? We can replace E with the Q. So the charge on the electron, and that is equal to 1.6 into 10 raised to the power minus 19 coulomb. And Vd is the drift speed, right? Drift speed. So electrons are drifting, drift speed. And finally, the drift speed, the value of Vd, right? If we calculate that will be equal to I by NAE, right? So if we put the value of current, put the value of N and A and E, right? So Vd, that was nearly equal to 5.5 into 10 raised to the power minus 5 meter per second, right? So this was the value of drift speed. But you see, drift speed is so small. It is in 10 raised to the power minus 5. So the electrons, they are drifting opposite to the current. So this is the drifting of the electrons. So electrons are drifting with the drift speed Vd, just opposite to the electrons, and that is so slow. Now, how it is possible when we turn on the light? You see this lamp. So in this lamp, if I turn on the light, so instantly the light is glowing, right? So how it is possible? Because the electrons in the wire, right, they have so small drift speed. The electrons in the wire, they have so small drift speed, but still, why? How it is possible for the light to just glow instantly, right? So the next question is that even after having a very small drift speed, right? So even after having a very small value of Vd, which is nearly equal to 5.5 into 10 raised to the power minus 5 meter per second. So even after having a very small value of drift speed, how it is possible for the bulb to glow instantly? How it's possible for a bulb? How it's possible for a bulb to glow instantly? So what is the answer of this question? If we consider the drift speed, then in terms of drift speed, we cannot explain how the bulb is glowing instantly, right? There is another reason also, and the reason is the electric field, right? So we have to explain this question, we have to describe this question, we have to answer this question in terms of electric field, right? Electric field. So actually what happens? So when we take a wire and it is connected to some source, voltage source, right? So definitely the current start moving from the positive terminal towards the negative terminal. So this is the current, right? So this side becomes positive, right? This side becomes positive, this side becomes negative. So you see, in this wire of some length, electric field is established, right? Between these 2 points. Let me take this point as P and this point as Q. So between P and Q, electric field is established, and let me take the electric field as EPQ, and this is a vector quantity, right? So this electric field is established, and this electric field accelerate the electrons, right? This electric field accelerate the electron. So all the electrons at their own place, right? Everywhere electrons are there. So every electron at its own place get accelerated, right? Suppose this electron is accelerated, right? This electron is accelerated. So very fastly this electron will just reach here, right? So it will contribute for the conductivity, right? Suppose you take this electron, right? So depending upon its position, it will be accelerated, right? The electrons which are very close to the positive side, they get more acceleration as compared to the electrons which are far away, right? So all the electrons in every part of the wire, they get accelerated, right? So due to that acceleration produced by the electric fields, there is a huge contribution to the current, right? There is a contribution to the current, fast contribution to the current, instant contribution to the currents, and that's the reason how the electric bulb glow instantly in spite of having a very less drift speed. If we try to explain our answer in terms of the low drift speed, then what will happen? In that case, the moment I turn on the light, right, the moment I switch on, the bulb will glow after few seconds, might be possible that after a few minutes, right? But in real sense, it is not happening. The moment we switch on, instantly the bulb glow. So that the reason is the electric field, not is the drift speed, right? So if we want to explain how the bulb glow instantly, that is not in terms of drift speed, that is in terms of electric field. So electric field that accelerate the electrons, right, at every part of the wire, right, and those electrons, they contribute the instant current, right? The acceleration of the electrons that contribute for the instant current, right, and that instant current that glows the bulb, right?